Saxon Algebra 1, Lesson 73. We have two topics today. They're both pretty direct and to the point. The first one is called factoring the difference of two squares. Now let me back up just a little bit and give you an example of something else that we know how to factor. We've learned how to factor trinomials like this, right? And we've learned, oh, you'd write the binomials like this, and you know when x goes here, and then you look for the two numbers that multiply to this and add to that, and we can see that this one, the numbers are 2 and 1. So then we write an art project like that, right? This is called factoring trinomials, and it's got a lot of steps, and it's not horribly difficult, but you have to use your brain quite a bit, right? Well, this is factoring trinomials. Okay? You already know how to do that. That's not what we're doing today. What we're doing today is, and by the way, the whole process starts by seeing this arrangement and recognizing that this expression fits a certain pattern. It has the x squared, the plain x, and the plain number, and remembering, oh, I know how to factor that. I set up the binomials, I find the numbers, blah, blah, blah. What we're going to do today is look at a different pattern. I'm writing three separate expressions here. They don't talk to each other. But I want you to notice something about all three of these binomials. I'm going to give you a second to finish writing that. I go too fast, I know. Okay, I hope that as you're writing these, you're noticing two interesting facts. The first one is that they all have a minus sign between them. Positive number at the front, minus sign in between. All right, that's interesting. Then the other thing I want you to remember is that, or notice, is that both terms in the equation are perfect squares. Perfect squares, right? X squared is x times x. Y squared is y times y. 4p squared, that would be 2p times 2p, right? X, y, 2p. I'm writing down what the perfect square is. 25, what's the perfect square of 25? Oh, 5. M squared, m. 16 is 4 times 4. Okay? So that's the two things that we notice. The minus sign in between and the perfect squares that I circled, all right? When we see that pair of characteristics in an expression like this, we know that we have what's called, oh, I didn't write it the way I wanted to, difference of two squares. The word difference relates to the minus sign that's in between them. The two squares relates to the fact that both values, whether they're letters or numbers, but they are perfect squares. That is the fact pattern that we need to notice in the beginning, just like we know how to notice this. As soon as we notice this, there's a super easy way to factor it. We don't have to do work like that. Once we see that we've got this pattern, we can factor it like this. And I'll show you some examples. I know that doesn't make sense yet. Just copy. And trust me, we're going to do 4 quick examples to show you how fun this can be. All right. I'm going to copy this to the top of the next page. All right, let's do examples. Factor. Now this is what John shows us. All right. What we notice right away is, well, we've got a perfect square and a perfect square, but the minus sign is not in the middle. So we have to rearrange this in order to get it to fit this pattern. As it is now, we can't factor it. But we can rearrange this. We don't have to swim any fish because there aren't equal signs. We literally just rearrange it, but we have to keep the minus sign in front of the 4. So we turn that into x squared minus 4. Okay, now this fits the pattern of a squared minus b squared, right? X squared is a perfect square, 4 is a perfect square. In order to factor this though, we need to know the values of that, the root, if you will, right? The square root of x squared is x. The square root of 4 is 2. Do you see what I'm doing? I want to use this pattern to do my factoring. So I have to make this look like that, right? If x squared minus 4 is the same as a squared minus b squared, which is what I've written here, then I want to find out what my a and b value are so I can write it like that. So now I write x minus 2 quantity, x plus 2 quantity, and this is my answer. Easy and fun. The only hard part is you just have to find the square roots and identify them and then make them fit the pattern. All right, here's the next one. 49. Okay, 49 is 7 times 7. M squared is m times m. A squared is a times a. Okay, I can figure out, these are both perfect squares. There's a minus sign in between. This one is what we consider our a squared. Right? I can always write this underneath just to remind me. This is the pattern I'm trying to fit. So the root of this one is going to be 7m. And the root of this side is going to be a, which is confusing because our pattern has an a in it on the other side. But that's okay. We just roll with it. Now we're ready to do this. And I go 7m minus a quantity, 7m plus a. P.S. because we're multiplying up here, it doesn't matter which quantity goes first. I can do a plus b quantity, a minus b, or I can do it the way I did here. And you'll notice over time, I'll mix that up. I usually do the minus first, but it doesn't matter. Okay. I hope the light bulb's coming on for you. Here's another one where John is being kooky. We see perfect squares, right? 36 and 25, that's 6 squared, that's 5 squared. Obviously, we could find the root of a squared and y squared. It's easy, right? But this minus sign is wrong. John has toyed with us again, so we have to rearrange. Again, we're not swimming anything, so the signs are not changing. We just have to put the other one in front. So it's 25y squared minus 36a squared. Okay, then this is our a. You don't have to write this under every time. I'm just doing that to make sure you can see what I'm doing. If 25y squared is the square, then the root of that is going to be 5y. And this is going to be 6a. So then I can write 5y minus 6a, 5y plus 6a. Gracie's licking her feet under the table. She's done a lot of foot licking this weekend with all the snow clumping up in her little paws. Grace, stop licking. I've gone out of order in these. I skipped one somewhere, I think. 1, 2, 3. Oh no, I'm okay. Oh yeah, I see what the problem is. All right, now I'm just going to show you real life handling of this. Here's example 73 for factor. Again, I see John has put the minus first and the plus second, and I know I want this term to go in front so that the minus sign is in between. So I'm not gonna copy it wrong out of the book. And you don't have to do that for your homework. When you see that he has messed with the order, go ahead and fix it as you copy the problem. We don't need to kill ourselves here. All right, so I'm copying it correctly in the correct order. 49a squared minus 36 x to the 6th, y to the 4th. All right, now this one's a little trickier, right? This looks kind of confusing down here. Let's do the easy part first. Again, this is the a squared and that's the b squared. So we'll figure out what our a is equal to and our b is equal to. Okay, a, the root of 49 is 7. The root of a squared is a. That was easy. Okay, let's do the number over here. 36, that's 6. Now, x to the 6th power. If we want the root of that, that means we want two numbers that will add together to give us 6, which sounds a lot like x cubed, and we'll check this in the end. And then this one, we want two numbers that add together to give us 4, so that will be y squared, okay? That's how you find the root of an exponent that is greater than 2 is divide it by 2, right? 6 divided by 2 is 3. Y divided by 2, or y to the 4th divided by 2 is 2. Okay, now we can write our expression, and then we'll test it to make sure we were right. 7a minus 6x cubed y squared, 7a plus okay, that is our answer. Now, when we go to multiply these back again, and we would do that by doing the dance. It's a long and complicated thing, but let's just look at what would happen. When we multiply bases that match and have exponents, we would add them. So x to the 3rd times x to the 3rd would equal x to the 6th, and that's exactly what we're looking for, okay? So what we're using here is the product rule in reverse, knowing that if we have a 6, then we will eventually add the two exponents, so we want 3, because then we'll do 3 plus 3 equals 6, and 2 plus 2 equals 4. Okay, so we're using, we're dividing by 2 to get those. That will allow us to add. And that reminds me to remind you that this week I'm going to have each of you guys retake this review problem because this rules for exponent charts was not firmly in your brains yet. Make sure you memorize this exactly the way it's written. Exactly, exactly, exactly. If you don't have this in your notes and you haven't been working on this, right now, pause this video and copy this exactly and start memorizing it hardcore. All right, we have one more bit to lesson 73. And we're going to go back to our probability topic. It's part B, and it's called probability without replacement. Most students find this interesting and kind of fun. We're going to go back to our example of the marbles in the urn. Okay, remember urns are those fancy things. Your moms might have some around the house somewhere with dried flowers in them or something, you know. They look like this, kind of. That's a very rudimentary cross-section of an urn. Okay, an urn contains 3 black marbles and 5 white. Okay, I'm going to draw them. Mine are kind of orangish, but pretend. right? Colored in ones are black. Okay, because orange is the new black. A marble is drawn at random and replaced. Then a second marble is randomly drawn. A, what is the probability that both are black? Okay, the probability of taking a white one, oh no, black, I'm sorry. Pulling a black one out of here would be 3 out of 8 in total, right? And that would be the first time. And then we're doing it the second time in a row. The second time it would also be 3 of 8, right? Because we took the first marble out and then we put it back in. Okay, so the probability that both would be black is 9 out of 64. All right, but now we're going to change that. And we're going to say, what is the probability that both are black without replacement? And I'll explain what that means. What that means is that we reach in, we take out a marble, we assume that it's black, so it's 3 out of 8. But now we want to know what's the probability, and we don't put that marble back in. We set that to the side. So now our urn looks different. And I don't mean the urn technically, but what's inside of it. Now we have 2 black marbles inside, right? We're assuming that the first one we took out was black. So now we have 2 out of 7. On our second go, because we did not replace the first one. The first time, it was with replacement because we put it back. And we didn't write that or say that because that's the assumption we've always been making. This is the first time we've taken a marble out of our experiment and not put it back in. So that changes the probability to 6 over 56, and those can both be divided by 2. That's 3 over what, 28. Make sense? So now we can find probability with replacement or without replacement, and we have to pay closer attention to our stories. Here's one more. That was, I think, 73.5. Yes. Here's 73.6. An urn contains 4 red. I'm not going to draw an urn this time. You'll have to draw your own. 4 red marbles and 7 blue. And I immediately just find out what the total is because I know I'm going to need that. 2 marbles are drawn at random. What is the probability that the first is red and the second is blue if the marbles are drawn A, with replacement, and B, without? This is the way John usually sets up these problems, is he makes you do it both ways, which is fine because they're not that hard, right? We could be simplifying something with a bunch of exponents and x's and distributing. That would be a nightmare. This is pretty easy. Okay, with replacement, we'll do that first. First, we want to know the probability of drawing a red. That's 4 out of 11. That's our first scenario. And then we want to know the probability of drawing a blue. We put the red one back, so we still have 4 reds, and now it's 7 out of 11, right? That's our second act. And so our combined probability of getting a red and then a blue with replacement is 28 out of 121. All right, now we're going to do the same thing, probability of red and then blue, without replacement. So the first time is the same. We reach in, there's 4 reds, there's 11 total, so that's good. Now we take that red marble and set it aside. So now we only have 3 red. We still have the 7 blue. So that means when I go to drawing my blue, it's 7 out of 10 total. So that's different. I'm going to reduce before I multiply. That's 2, that's 5. So it's 14 out of 55. Make sense? I can just hear you saying yes. Oh, I have been neglecting my smileys. These are all right though. I've been checking as I've been going. Yay, that's the end of lesson 73. Factoring the difference of 2 squares, which requires you to memorize a formula, but is pretty darn fun once you get to it. Probability without replacement means that we now have to work our problems in 2 steps, but that's okay, they're easy and fun. Okay, that's the end of 73. Go play in the snow if it hasn't all melted. Goodbye.